of course, I wish I were here at the Bell Center, coming to you live from Montreal. Let me share my screen, please. There we go. So I don't think I need to tell you, but I'll just remind you that there's a lot of hype in exoplanets about small exoplanets.
It's what's called a super Earth.
A super discovery outside of our solar system. It's a super Earth.
Elle s'appelle Kepler 452b. C'est une exoplanète. Elle a des caractéristiques très proches de celles de la Terre.
Earlier this week, NASA announced the discovery of a possible Earth-like planet.
So indeed, this is this gold rush, and it's not just like a media thing. I went on today, I was just doing a standard internet browse, and went to ADS. There's like 1,000 guys, papers with Super Earth in the title. This is this new burgeoning field that's really been growing over the past 10 years. And my cat just turned off my screen. And indeed, I think a lot of the hype is justified. If we look at the planets, look at how they've been found, if we look at the solar system for comparison, we can really see, I'm just going to move this away from you. You're looking at that like you're going to step on it again, okay? We see this distribution of planets, and we see lots of them in this regime, which I'm just going to broadly call super Earths. Anything between roughly Earth and roughly Neptune. There's definitely sub-distinctions, but just roughly things that we don't find in the solar system. And indeed, I think that, this is really a gold rush. We're talking about these brand new systems, unlike what we see in the solar system. We're thinking atmospheric characterization with JWST, maybe Ariel in the future. We're thinking maybe little green men in the habitable zone. And these are all, super important, interesting pursuits. What I am looking at this as is I'm seeing a lot of question marks about this new population of super Earths. In particular, I'm going to pose the question of where do hot super Earths form? I say hot because these are transiting planets, so they're typically quite close to the star. And so from a simple point of view, some would say, okay, well, they form in a protoplanetary disk, yes. But where exactly in that disk do they form? Very simply put, with these absolutely amazing graphics, do they form in situ, or do they form farther out in the disk, maybe near or beyond the snow line, and migrate inwards? And this is an interesting one in the field of exoplanets because it's something where it's a lot of work has been done on, let's say, roughly both sides. Of course, there's a lot of overlap, but I think that there are lots of open questions here. Now, I will preface this by saying I am not a planet formation expert. You're very lucky you've got Eve Lee here in particular, planet formation expert. And I don't have a particular team here, let's say. What I'm going to do with this problem is I'm going to approach it from the point of view of, well, can we conduct an experiment where we could switch off in situ formation? I'm not saying it's wrong or anything like that. I'm saying, could we turn it off? So for this experiment, we need a laboratory. And so I'm going to use the astrophysics equivalent of a laboratory, binary stars. They're the things we use to calibrate our stellar models. They're what we use with type 1 supernovae to map the distances in the universe. They're what we use for gravitational waves. I'm going to use binary stars to try and probe whether or not super Earths form in situ or via migration. In particular, I'm going to use binary stars like this, which actually have a planet around them. This is Kepler-16, an example circumbinary planet. This was discovered by Kepler, and what you're looking at it is how Kepler saw it, i.e. edge on, where the two binary stars are eclipsing each other, and then the planet, basically 90 degrees aligned, is going to transit in front of both of the stars. If you instead look at it face on, you're going to see the two stars undergoing their wobble, their little orbit there, and then the planet is going to go around the common barycenter. So how do I use this to probe formation of planets? Well, this is what we think that protoplanetary disk would have looked like around a binary. We see that close to the binary, at a separation of roughly 2 to 3 times the binary separation, a big hole has been carved. It's a big cavity in this disk. And this is just due to the tidal interaction with these two stars as they go around in their orbit. Interestingly, we have found about a dozen planets, and most of them have orbits which would basically correspond to here. They've all been scaled, and basically those planets' orbits are about as close as they could be to the binary. In particular, they're very close to where that disk would have been truncated. So what's this got to do with in situ formation? Well, we're not going to form planets in situ inside this black region here. There's nothing there to form a planet with. It is also believed that we do not form planets where we currently see them, where, yes, there is a disk, but it's highly turbulent. The relative velocities, the collisional velocities are really high, so things tend to shatter apart rather than stick together to form a planet from the ground up. And you always have to worry about the binary ejecting things that get too close to it. So we really have this strong belief that circumbinary planets form farther out and then they migrate in. And this theory is strengthened by the fact that a migrating planet will tend to be stalled near a steep pressure gradient, a steep density gradient. And that's what indeed we have here. We have this very steep density gradient because basically a wall has been carved in the disk. So I'm going to say that circumbinary planets only form via migration, with the little asterisks that, let's never be too definitive, but this is the running theory I'm going to have. So based on this, I propose a hypothesis for our little lab experiment. Circumbinary super-Earths. If they exist, then I will hypothesize that super-Earths form via migration in general. On the other hand, if they do not exist, then I will hypothesize that super-Earths form in situ, but this process is impossible around binaries. And that is where we lead us today. Circumbinary super-Earths. Do they exist and how do we find them? At this point, je vous remercie pour cette invitation. Je suis triste que ce n'est pas possible d'être en personne à Montréal. C'est une ville incroyable, mais j'espère la prochaine fois. So, I am David Martin. I'm a postdoctoral fellow at The Ohio State University, and I'm very, very happy to be here. And I really hope that the next time I can come to Montreal. It's one of my favorite places to visit. Absolutely beautiful city. Circumbinary super-Earths. Well, before we ask the question of do they exist, let us ask a subtle but importantly different question. Have they been found? We have this size distribution of planets around single stars, corrected for observational biases. And we indeed see that there are lots and lots and lots of small planets. I'm talking 2 Earth radii, 3 Earth radii, compared to these big gas giants at, say, 6 or 10 Earth radii, like Jupiter and Saturn. Let's put in a line here for a circumbinary planet discovery. And let's just fill this in. I told you we had about a dozen. So let's fill this in. What we see is that we've actually only found circumbinary planets down to about 3 Earth radii, i.e. at radii bigger than, say, a super-Earth. So to simply answer this question, no, we have not have circumbinary super-Earths been found. The answer is no. But the important caveat is to say, well, could they have been found? Based on how those dozen were found, would we have found super-Earths? The challenge is that if you want to find something small, let's say even an Earth, even more challenging, it looks like this to scale. And so even if you have a state-of-the-art telescope like Kepler, a typical Earth transit may look like this, and it just looks like rubbish. It just looks like it's flat, okay? It's like nothing. The way in which we managed to find those hundreds and thousands of small planets around single stars was by just a method of phase folding, which means that you take a lot of transits, you assume periodicity, and then you phase fold the data on top of it. So it stacks together coherently, and you can use the magic of root n, where n is just the number of data points. And so yes, one transit looked pretty crappy, but 10 transits, pristine. Now, why could we do that so well around single stars but not binaries? Well, the challenge is that the planet is transiting a moving target. And so whilst the binaries have a large range of positions at which they could be transited, this corresponds to a large range of times. Furthermore, you don't just have three-body geometry complicating things, but you have three-body dynamics. The orbit of the planet, for example, will have an apsidal precession, plus other effects of higher order. So the consequence of all this is that your transit timing variations are not seconds or hours like you might get around a single star, but we're talking days. We're talking transit timing variations that are larger in amplitude than the length of the transit themselves. And just to complicate matters, those transit lengths also vary. So the consequence is that if you just wanted to apply the technique that was so successful around single stars to binaries, i.e. you phase fold on a fixed period and a fixed duration, you would just wash away your signal. So all of those 12 planets found to date were done so by eye. They were done by people with incredible eyes looking through a couple of thousand eclipsing binary light curves and literally looking for that tertiary transit, which could be due to a planet. And I must say, I mean, the human eye is incredible at finding patterns and does an amazing job here. But the one weakness is that you do require each individual transit to be visible. And this means that you're only really going to be sensitive to the large planets. So could they have been found? I'm going to say in the large majority of cases, no, they could not have been found. So that non-detection is actually not really meaningful yet. So how do we find them? So part of my work recently has been to work on a new method where we fold on a variable timing and variable duration such that we can coherently stack shallow transits, multiple shallow transits, in the hopes of finding small planets. And indeed, this is what we call the Stanley automated algorithm. And this is work done in collaboration with Daniel Fabrici. Just to make sure there's no confusion here, that's Dan in the front. I'm at the back. We had a little socially distant work date in my front yard. And Stanley's a dog. It's not an acronym or anything like that. I didn't try to force an acronym. I just wanted to name it after my dog, and I did. The joys of being the first author. So at its core, this is really just conceptually quite simple. It's an n-body brute force grid search. Imagine your light curve with this thing in blue, flat bunch of transits. What I'm going to do is I'm going to have this huge grid of different parameters, and at each one I'm going to create a mask. And I'm just going to keep trying to fit that mask. I'm going to keep trying until I find something that works. And bang. There are my different transits. I'm going to pick out where the transits are in a certain window. And I'm going to scale the transits based on a variable duration, fold them together, and voila, I've coherently stacked them. Conceptually rather simple. But as anyone will know, in astronomy and astrophysics, often the devil is in the detail. So let's consider some of the difficulties of this. For starters, speed. It's slow. If you want to encapsulate the three-body geometry and the three-body dynamics, you're having to create an m-body simulation to run over the, let's say, 4 years of Kepler data for every single point on your grid. So it's slow. Another challenge is you need precision, i.e. precision in that grid, such that you can hit that very sensitive, that very specific set of parameters that will match the transit timing. Because it's like a barcode. A transit time of a circumbinary planet is a bit like a barcode. It's very specific. 3, you can have an infinitely precise grid and a million CPUs or whatever you need. And if your light curve looks like crap, your answers will be crap. And there's a lot going on in light curves, and so you have to be very careful to remove the things you don't want, but to keep what you do. And finally, false positives. Anyone who's ever dealt in observational astrophysics will know the challenge of false positives. The thing that really scared me, and this is probably the reason why I didn't start this project during my PhD, was I looked at the parameter list and I got really scared because we've got 2 Keplerian orbits, so that's 6 times 2 orbital elements, plus 3 bodies, so that's a mass and a radius for each of them. So we're talking about running a brute force thing over a grid, 18 parameters, 18 dimensions. It was just not feasible. I'd say one of the tipping points that made this possible was by really looking in and doing two things. One, we could figure out which parameters we could ignore. These are the ones that have been crossed out. And two, we could actually leverage the work of other people in the community. So these parameters in here in blue for the binary, these were actually known in the Kepler eclipsing binary catalog led by the folks at Villanova. And we leveraged that. And that's been around for a while. The big new advent was Diana Windemuth, who was a grad student at Washington working with Eric Agel, and they did great work to characterize the masses and radii of the stars in the eclipsing binaries, even in the absence of radial velocities. Now, they're not going to be as precise as if you had radial velocities, but they're applied to a large sample. And what we found was actually they were precise enough. So now we're basically down to 4 parameters, and maybe this problem could actually work. But even then, we have to be careful. We have to make sure that our grid is sufficiently precise to hit that barcode, that transit timing signature. And so we did a couple of little bespoke things there specific to circumbinary planets. We basically predicted how long the durations would be, and then we constructed our grid accordingly. But then, of course, here comes the real challenging one. How do you get rid of all that pesky stuff in your light curve? I.e., how do you go from this red curve and fit that, or these red dots, and fit that black curve through it, such that you're left with the red, so you're left with the blue, such that you have flat and then a little transit dip, flat with a little transit dip. And that's the absolute challenge here. And just to put things in perspective, these are the type of things that could cause variations in your light curve that aren't just a transit. For example, we're dealing with eclipsing binaries. And yes, eclipses are really obvious, and you can pick them out very easily and you can remove them. But that actually is going to create all these gaps in your data. Furthermore, you're going to have stellar variability and rotation, things that you do get in single stars, but here you get it ×2. Then you also get these binary specific effects like Doppler beaming / boosting, however you want to call it, ellipsoidal variation, reflection, and those things occur basically sinusoids on the binaries period or some integer multiple. And then on top of all this, you have this challenge of, I'll go back, a variable transit duration. Because we want to get rid of basically everything that's not a transit, but the thing we want to keep keeps changing how it looks. I'll show you an example here where we can see some of these effects. These are the transits of Kepler 38, Kepler 38's circumbinary planet. We can see in the top panel, a bunch of those transits are blended with the eclipses, both the primary and the secondary eclipse. And on the bottom panel, we can see quite clearly how the duration of the planet's transit keeps varying. And you might have noticed this, a keen eye might have noticed this phi value. Phi is actually the orbital phase of the binary. And if it's near 0.5, you get really long planetary transits. That's because the star and the planet are moving together on the sky. And if you're near phi of 0 or 1, you get a short transit because they're moving against each other on the sky. So what we had to do was basically develop this new method of detrending, where you're detrending how aggressive you are in removing frequencies in your data, changes based on how the transit duration changes, such that you can keep both long and short transits. And then, of course, false positives. Well, here's something that scared me. This is a little thing we did early on. What we did was we took 270 eclipsing binaries, detrended them, and then we looked through just to find the 9 times according to the deepest flux. Then we just created a list of 270 times 9 deepest flux points and created a histogram. What we see here is that there are certain times in the Kepler light curve which appear as a deep point in flux across many targets. I'm talking, potentially almost up to half of the targets have a deep point here. And this is actually after being quite rigorous in terms of cutting with respect to like data quality flags to try and remove some of the crap. And furthermore, these deep points aren't just any old deep points in flux. They actually look like transits. This is an example here. This is about 112 days. And we see just 3 example light curves where it looks like a transit there. And the reason why we ran this experiment was that on earlier versions of the detection code, I kept finding these transits like, oh, hey, here we go, found a new planet. And no, it looks suspiciously like the transit I found in another light curve. I can't tell you the exact cause for all of this. I do know that this is across the entire detector. It's not like just one bright blended background star bleeding out. But this is definitely a challenge. And we basically just cut out all of these. But okay, putting it all together, this new method, does it work? Well, Kepler 16, this is actually that little video I showed at the start. Here are your example transits. And the algorithm intelligently detects them by labeling the in-transit points in red. But of course, you could have seen this by eye. We can see here that grid. So it's a function, at least 2 of the dimensions, is a function of the planet's period and theta. I'm going to show the signal to noise ratio. And you see it's just a sea of blue. Most of your fits to the data are absolutely awful. Except if you zoom in, you get that tiny, tiny little needle in a haystack, which manages to fit the data basically perfectly. What you may also see are these little white lines. These white lines with a slightly higher signal to noise ratio, those will correspond to individual transits where your fit has fit and your models fit an individual transit. And since the transits are so deep, they actually do stand out above the noise. As a little historical detour, Jenkins, 1996, actually developed a quite similar method. And I wish we had found this paper earlier on, but it was quite cool to see that a very similar thing here. Now, the reason why maybe we could have a little more success with the method now versus back in 1996 is quite simple. We've got much faster computers and we have the Kepler Space Telescope. So now if we collapse that grid down into one dimension, so as a function of planetary period, what is, I'm going to call the signal detection efficiency. It's a bit like a BLS statistic, but it's basically if periodogram, is there a big spike there? And if that spike's above 8, I'm pretty happy. And here at 14,000, I'm probably pretty happy. I think we're quite comfortable we've found the planet here. You also see some spikes at, let's say, 2 times the period. These are just aliases. Let's go a little more challenging. Here's Kepler 34. We see an example transit up in the top right. Again, you could find that by eye, but it was found quite convincingly here with Stanley. Kepler 64, it's getting a little more challenging. We can see the transit's still obvious by eye, but it's going towards the noise, but again, still pulled out by Stanley. Now we go to what I'm going to say is basically the precipice of the limit of by eye detections. Kepler 47, this is 3 Earth radii. And you can see that transit is barely above the noise. But with Stanley, we're able to detect it at a signal detection efficiency about 15. So it actually was quite a strong signal, despite being the limit of by eye detections. And furthermore, this system is quite cool because if you remove all of that data at this 50-day period, you actually see a residual spike because there are also transits at a 300-day period. And then if you remove that, you can see that there are transits at 187 days. And notice these guys were all found by eye, but it was quite a nice demonstration to be able to see that we could actually iteratively find more and more planets. And then, of course, if you remove all of them, you basically just get white noise, which is what you would hope, particularly if you detrended the data well. So at this point, I would say, how do we find them? I believe that this Stanley algorithm can work well. Now, I'll give a little quantifier here, though, that also Diana Windemuth, who I said did that great work characterizing the binary stars, she also developed an algorithm essentially for this purpose, an automated circumbinary planet finding algorithm. And it's really cool because it actually approaches it in quite a different way. So the two complement each other. But I'm happy to answer questions on any differences, but I'll leave that to that. But okay, now this is really the new stuff. Now, really, have we found any yet? So this is work done just over this summer with a high state undergraduate, Hannah Parsons. She did great work first to further optimize the detrending, try to avoid situations where you eat up some of the transit depth by poor detrending. She really improved that. And then what she did was she basically ran Stanley on hundreds of binaries. And this takes a long time as a computing cluster, and she put in a lot of great effort here. So, drum roll, how many planets did we find? We ran it on 432 binaries, and we found 13 planets, which I was pretty happy with. 13 planets out of 432 was pretty good, I thought. Except when you realize that out of those 13 planets, 12 of them were the ones that had already been published. And then there was one which is admittedly not published, but I already knew about it. I already knew from collaborators. It's in email chains, so I would not want to claim that as our own new discovery. So, being honest, no, we might have a couple of candidates, but nothing I would be comfortable to show now, because we're just really just very, very vague candidates. I would say right now, being cautious, no new planets based on this search. But again, of course, we have to ask the question, could we have found them? Well, there were two ways to test this. First, what we did was we scaled the known transits, meaning that we went to all of the light curves of the known circumbinary planets, and we took their transits and we made them shallower, preserving the noise properties, but made them shallower. So we could test, let's say, Kepler-16 if it weren't the size of Saturn, but were rather 2 Earth radii. So now a transit looks like this, again, actually pretty obvious by eye. The SDE has gone down, but is still large. And we can see this kind of, I think it's kind of cool, like rivery plot. We can see you've still got that little needle in a haystack, but those individual transits, these white lines, do still show up above the noise. But the cool thing, which is really what we developed Stanley for, was when you go down to, say, 1 Earth radius. Suddenly the transit is not looking much different to noise, but we can have this admittedly marginal, but actual detection at a bit, SDE a bit above 8. And we can see here suddenly individual transits are noise. They don't stand out at all. You really have to get that tiny little needle in a haystack in order to find the planet. And so by testing our sensitivity with this way, we discovered that these are the known radii, but these are the radii with which we could have found them at. I.e., for about half the system, we could probe down into this super Earth regime. Now, the second way in which we did this was a injection retrieval, so a more classic thing, where you take a known light curve and you inject planets at the very first stage of detrending. So you then go through all of the detrending process, which sometimes can kill transits if you're not careful. And then we run it through Stanley, see what we can get. And through tests, this was again great work that Hannah Parsons was working with, we found about a 33% retrieval rate at 3 Earth radii, and down to, I'm going to be conservative and say about 25% at 2 Earth radii. So I would say that, could we have found them? I'm going to say, yeah, I reckon we probably could have, at least in a large chunk of them. And so now we can actually ask a question about, let's say, a relative abundance. Because we go back to this plot and we see that around single stars, small planets outnumber big ones 8-1. But curiously, in earlier work that I did with Amoy Trio and Dave Armstrong, we found that the gas giants, the guys that are rare around single stars, have a similar abundance around binaries. So now you might say, well, what if the small planets had a similar abundance? How many could we expect? So if we searched 432 binaries and we found 13 gas giants, then 13 times 8 is about 100. There should be about 100 small transiting planets in there. And if we are sensitive to, let's say, about a quarter of them, then there should be about 25 expected discoverable small planets. And we found 0. So at this point, this is definitely, what work we're doing right now to try and constrain this relative abundance between small and big planets and compare it between single and binary stars. I can't give you a quantifiable number right now, but I think I can say with reasonable confidence that the relative abundance is lower. By that, I mean small planets may be 8-1 more abundant than big planets around single stars, but around binaries, this is not the case. To finish this talk, though, I'm going to take off my observer hat and put on my theorist hat. And I'm going to move from do they exist to should they exist. I give this a real sort of quotation marks by saying it's always risky in theory and astronomy to say something should or shouldn't exist. You know, hot Jupiters should not exist. Super Earths should not exist. Circumbinary planets should not exist. But I'm still going, let's just make the prediction. Let's just have a look at should these guys exist. And I'm going to run through two potential reasons why they may not exist from a theoretical point of view. One, small planets migrate too slowly and will be ejected by resonances. I told you that most of the planets exist very close to where the disk would have been carved out. This corresponds to basically the stability limit. Any closer and they would be ejected. Now, the reason why you have these ejections is due to resonant overlap between mean motion resonances with the binary. By that I mean, let's say a 5-to-1 mean motion resonance means the planet goes around once and the binary goes around 5 times. Now, resonances can have stabilizing or destabilizing effects. In the solar system, Neptune and Pluto, 3-to-2 resonance, that stabilizes Pluto. That's what allows Pluto to survive. But these N-to-1 resonances around binaries are typically destabilizing. Now, if we look at this plot, these are the known systems, and we see that all of them exist off mean motion resonances. None of them are in resonance. But just because they're currently off resonance, remember, we have this paradigm where we think they formed farther out and migrated inwards. Therefore, they had to migrate through these resonances. So Kepler-16, which is this blue dot at the bottom right, it's at a period ratio of 5.5, but that means it went through the 6-to-1 resonance and the 7-to-1 resonance and so on. Now, what this has to do with circumbinary super Earths, and indeed small planets in general, is that the migration speed of planets, at least in the type 1 regime, is believed to be proportional to the planet's mass. So smaller planets migrate more slowly. Therefore, smaller planets are going to spend more time near these destabilizing resonances, and therefore might be preferentially ejected, which would explain why you do not have small circumbinary planets. But let's run this through though. So this is basically the idea. Then we started to do the work. What I'm showing here is from Billy Qualls, a stability plot. So I'm plotting as a function of the planet's eccentricity and semi-major axis. And the pink basically means stable, and the white is unstable. And for Kepler-16, we can see this little green dot where the planet is currently found. And you can see these little streaks. These correspond to resonances. And so indeed, the 5-to-1 resonance, just in front of it, fully unstable. No matter how circular that planet is, it would be unstable at that 5-to-1. But you can see at the 6-to-1, 7-to-1, 8-to-1, and so on, the instability does not go all the way down to a circular planet. That means that if the planet migrated and maintained a small enough eccentricity, it would actually be okay. And you can see the same for Kepler-64. And so what we did was we looked at all of the known planets and we created this map. What this map shows you is, as a function of the binary's eccentricity and mass ratio, what is the lowest order resonance, which would be at least partially stable. So if you had a super circular binary, then even the 4-to-1 could be okay. And if it's a bit more eccentric, the 5-to-1 in yellow, then the 6-to-1, and so on. And then I looked at where the actually known systems fit in here. And then I color-coded them based on their known period ratio. So Kepler-16 is this guy here. It's got a period ratio of 5.5, so I've put it in yellow. But it's in this regime where the 6-to-1 would be stable. So it actually didn't have to go through any unstable resonance. And what I found out was that all of the known systems, none of them are interior to fully unstable resonances. So this argument perhaps does not hold. So then what we did was we actually simulated it. We created an n-body simulation with prescriptions for migration, including both a Lindblad torque to bring you in and a co-rotation torque to balance you near the pressure gradient. And we found that all of the known systems, these are all the known 12 systems, I can get them to park exactly where they're found, no issue with resonance, no issue with how fast or slow you go. But here is maybe a little caveat. Imagine if it's a big night out, Montreal has just won the Stanley Cup, finally, and you just had a couple of fin du monde and you're sort of walking home, and it's not this like straight path like you're avoiding this eccentric region, but it's more like this. It's like this migration path, you're having your eccentricity fluctuate over time. Then you actually run the risk that suddenly that 6-to-1 resonance, which I previously said was all fine, might actually be unstable. And so we simulated this by implementing a thing known as stochastic forcing, developed by Hanno Ryan, now at University of Toronto. And it's basically simulating turbulence in the disk. So the planet, whilst undergoing its smooth disk migration, is also essentially undergoing a little bit of a random walk. And so in this simulation here, this is the exact same planet in each case. I'm just starting them at slightly different times, but where they end up should be the same, except for the fact that stochastically, some of them, I believe 4 out of 10 here, were actually ejected. That's because the stochastic forcing, whilst that itself is not going to depend on the planet's mass, the amount of time you spend near that potentially destabilizing resonance is a function of the planet's mass. And so some of them get ejected. So to summarize, and this is work working with Evan Fitzmaurice, an undergraduate at Ohio State, there may be potential instability of small planets under this migration paradigm where the small planets get preferentially ejected rather than the big ones. Now, this is actually work that really spun off Evan's work. Evan recently graduated. He's now a postback, back working with me at Ohio State. His thesis was not on this. This was the spin-off of his thesis. He did such good work, it spun off another bit of work. His thesis was on this second possibility. Small planets could be ejected by migrating giants, like the giants we've already seen. So recall, we believe that you have a disk and it's got some gas going around it, and then the planet forms out here and it migrates in. That's what we believe. But what happens if you also had another one? And what happens if that other one were bigger, like a gas giant? Or if it were smaller, like an Earth? Well, this is the topic of Evan's undergraduate thesis, which is now going to be turned into a research paper. Let me walk you through this one example here. There are 2 planets in this system. So each is a pair. So the yellow and the orange, the red and the pink, the green and the green, the blue and the blue. Each pairs of planets in different situations. In each case, the inner planet is the exact same. And all the inner planet wants to do is migrate down and park near the truncation of the disk. What changes, though, is the outer planet. In the yellow, the outer planet is 10 times the mass of the inner one. In the red, it is equal mass. In the green, it is 1/10, i.e. it's a smaller outer planet. And in blue, it's 1/100th. What we see in the yellow and red cases is that innermost planet does come down and get towards parking at the disk. But what happens is the 2 planets enter a 2-to-1 resonance. And so even though that inner planet wanted to stop migrating, it's now actually being forced even closer to the binary by the fact that the outer, more massive, or at least equal mass planet does still want to keep migrating, and they're locked in this resonance. And that actually causes the planets then get ejected. So you can see it just flying up. On the other hand, if the outer planet were less massive, then yes, they come down and they get locked in this 2-to-1 resonance. But in this fight between which one is actually going to migrate in, the inner one manages to win, and the inner one manages to stay parked, and that causes the outer one to also park, but in this 2-to-1 resonance locking. So based on this work, we can make 2 predictions. One is that small inner planets should lack close, bigger companions. And this will also mean that in any case where you did indeed have a giant planet, that may eject small planets and cause their demise. And so again, this could be another explanation why we may not have small circumbinary planets. Furthermore, another prediction we might make is that large inner planets may have smaller outer planets locked in resonant configurations. And that's quite nice because we've just spent all this time trying to develop this technique to try and find new circumbinary planets. This gives us a target to look at. And so, as I said, this is a paper that will be coming out a little bit later, work with Erin Fitzmaurice and also in collaboration with Dan Fabric here at Chicago. But to summarize, I would say circumbinary super-Earths, do they exist? Should they exist? I believe at least now we can find them through development of the Stanley code and also, as I said, Diana Windemuth separate code. But I think that we can now, and this is admittedly the first time I've said this at a conference, I believe that we can say that they are rarer than expected. At least the ratio between big and small planets is different around binary stars than around single stars. And then we've gone through and tried to come up with maybe a few theoretical arguments why small circumbinary planets would not exist. And so at this point, I'd like to say thank you so much again for your attention. My name is David Martin. I'm a postdoctoral fellow at The Ohio State University, and I'll happily take any questions. Thank you. I don't know what do you normally pick out questions, or do you want me to just pick on the list? Or I'm happy with whatever.
I don't mind hosting the question period. So I see we have a couple of raised hands. Ronnie, do you want to go first?
Yeah, sure. Thank you for this great talk. As someone who doesn't know anything of exoplanets, it was a great talk. Really, I learned a lot. Coming to your later point on larger planets migrating inwards and ejecting the smaller ones, that sounds a bit like some of those formation theories about the solar system, the Nice model or something. Can't remember. Is the work you're doing, does that also help constrain sort of formation histories of the solar system as well?
Ooh, great question. I've actually never put two and two together, but you're right. I mean, this has a niche-ish feel to it. The idea that or Grand Tack or whatever, but basically giant planets, Saturn and Jupiter, migrate inwards and knock out the stuff which would have formed a super Earth around Mars, and then that's why we don't have a super Earth, because I guess we have to explain that because super Earth is so common. So yeah, I agree that there is a little bit there. I'd be lying if I said I was inspired by that, but that's an interesting connection to make. Then in terms of constraining the solar system, I'd say that what the best we can do is maybe just better understand super Earths in terms of in situ versus migration, and how people, and if this does argue one way or the other, how people can then apply that to the solar system. I'm honestly not quite sure. That would really be a theorist's job, but I'd be very curious to see if that helped them.
Okay, we have another question from Nick. Go ahead.
So what's next for Stanley? I mean, you developed this code and you named it after your dog, which means you don't want it to be useless. But if these planets turn out to not exist, like, did some of the work that you put into this very difficult task of finding smallish planets around binary stars, like, can some of that be useful for more run-of-the-mill transit timing issues, or I don't know, like, what are you going to do with this if it turns out these planets don't exist? Because it seems like a really impressive code.
Sure, thank you. So I would say, before I get to the plans, I would say even in the advent of a non-discovery, I am still confident that based on how many planets we would expect to discover, based on the fact that small planets are so much more abundant, that we would still have an actually very interesting non-detection, like an actually constraining one that would actually tell us a lot about these relative populations. So even in the lack of discovery, I would sort of be okay with that. In terms of, though, adapting it for the future, I mean, the obvious one is TESS. TESS has such large numbers that you would like something that's automated. The challenge, though, with TESS is that Stanley is all about, stacking together lots of transits over a long baseline, whereas TESS, as you know, is typically short baseline. So I would say that the next application for this would be TESS continuous viewing zone. But that requires a large sample of eclipsing binaries on which to test it. The lucky thing here is that I'm not really a part of it, but I have connections with the TESS eclipsing binary working group, and they've got tens of thousands coming up. So it's kind of whereas when I started Stanley, there was nothing like that. So it's kind of well timed to be able to apply it to TESS. And of course, the nice thing with TESS is that we can go get RVs much more easily because they're brighter.
Eve, do you want to go ahead?
Sure. Thanks, David, for the really nice talk. Towards the end of your talk, you mentioned these two theories and what you would expect. And for one of those, it was a case where if you have the inner giant, then you would have outer smaller companion. But if I understood the rest of your talk correctly, that you had the capability to detect these small planets, but you didn't. So do you already rule out that the second hypothesis, or do you need to retarget and look at it again?
That's a good, I guess for the second hypothesis, if we have this strong non-detection, then what I would conclude from the second hypothesis is that point number one is not so much that small inner companions lack close big companions, but it's more those big companions were very common and killed these. Mm-hmm. And so what would be interesting to do there would be to think, okay, how can we find those bigger companions that may be farther out, that maybe kill those planets? Maybe they're not, right at the stability limit, but maybe they're a little farther out. And that would be a case of, okay, maybe we look for radial velocities, because we also have a program trying to find circumbinary planets and radial velocities, and that's a bit easier to find stuff that's farther out. So that's how I would approach that from an observational point of view. But I agree that, that theory may predict that there are no small planets, and that would also predict that there are no small planets, even if they would have formed via migration. They tried to form via migration, they just got kicked out.
Mm-hmm. All right, thanks.
Mohit, you want to ask a question?
Sure, thank you. First of all, David, it's truly amazing talk. Thanks a lot. I do not work in this field, but I still digest most of the points that you have discussed. So thank you. So I want to go back to the big question you raised. So I think that question was where super Earths form, whether they formed in situ or are migrated to the inner orbits of I'm so sorry, of the stellar systems. So what constraints we can put on those two contesting theories based on the possible absence of these planets in the binary stellar system, basically?
So basically, if the small planets do not exist, then that would lead more towards in situ, because basically in situ is not going to work around binaries. At least I'm pretty confident. I think a lot of people are confident of that. So that's what it would argue to. However, with the caveat of those theoretical works I did at the end, which kind of muddy the waters, which kind of said that, oh, even if you did form via migration, you could still be ejected. So it's not cut and dry. It may also be something that comes down to, well, maybe there's a distribution, maybe there's a mixture of super Earths, some form in situ, some form farther away. A lovely discussion with Professor Lee earlier today about how the ones forming farther away might be more puffy. I have a suspicion that circumbinary planets might be a little more puffy than other ones, but that's a whole other talk. But yeah, that would be a sort of answer to you.
Okay, we have one question in the chat, which I'll read out loud. So how much of the bimodality and exoplanet radii distribution is due to the limitations of Kepler, TESS, or other exoplanet finding instruments?
Great question. So I maybe should have said that this is basically all Kepler. People will often tell you with respect to TESS that TESS is not a statistics mission. TESS is, in some people's view, an elaborate finder scope for JWST, so you can get the best targets for JWST. I still do some statistics with TESS, but most exoplanet statistics you're seeing are coming from Kepler. Then in terms of the biases, well, actually the bias would, as a simple point, actually work against finding the small planets. So this has been corrected for observational biases. The actual observed distribution would actually have a higher ratio of gas giants to small planets just because gas giants are easier to find. So I believe that this is, pretty true, at least for planets close to the star.
Do we have any other questions? Mohit, did you have another question, or you just didn't lower your hand?
I'm really sorry, I forgot to.
It's okay. Oh, I see one. So Loic, you want to ask a question?
Yeah, hi, very good talk, thanks. Just, I guess, as a follow-up, maybe far left question in the far left field. Can you say, have you estimated the number of ejected planets that would be free-floating in the neighborhood? I understand there's lots of binary stellar systems, so potentially lots of free-floating planets, ejected planets out there.
Great question. So I guess I'll pop back up this slide. It's probably the most relevant. So there have been studies of basically what happens to ejected circumbinary planet material. It's not really, you're not really saying how those planets become unstable, but just saying if they are unstable, what happens to them. And I believe it's about, so it's Sutherland and Fabrici circa 2016. Caitlin Crowder has also done work on this. You're talking about like 90% do get ejected. So most things do not hit the central stars, which some people maybe thought increased metallicity of the stars or something, but no, most things do get injected, like you say. Indeed, what would happen to them? I mean, they would be free floating bodies throughout the universe. I believe that I was told about papers even in like the 80s, sort of thinking that you could produce free floating guys like this, more modern, could you produce Oumuamua, things like this? I believe that this process we have here, like in the orange and red curves, where the small planet is sitting happy and then the big one comes in and kind of shoves it over the cliff, it seems to be a very simple, somewhat universal process. So maybe that could produce a lot, but in terms of raw numbers, I probably should be able to do like kind of a back of the envelope calculation to get some rough numbers. And yeah, maybe when we publish the paper, we'll try and do that. That could be interesting.
Well, if there are no more questions, I'd like to thank Dr. David Martin for giving us such a great talk with extremely entertaining slides, and for the little kitty there.
Blowing some kisses. Mwah. Mwah.
Cool. So if we could all just take a minute to just thank him, and